Okay, so in order to compare any polarities, you got to draw the Lewis structures. So I'm not going to draw electrons on the outside here just for the sake of this, but on the quiz you definitely need to. So that's a tetrahedral molecule. We see that Cl is pulling on the electrons in all regions. We have HCl. Okay, so we have partial negative here and partial positive here, but those all cancel. Partial positive here and partial negative here. So what I would write over here, which you don't need to write, you need to write, I'm not going to write it right now to save time, is simply that HCl is a polar molecule because the dipoles do not cancel out, and we are left with positive charges, partially positive and partially negative. CCl4 is a nonpolar molecule because all the dipoles do cancel one another out. Okay. Down here, same Lewis structure there for CCl4, but for this one, we're going to get this. Now we know that that doesn't count, but we got a dipole here, a dipole here, and a dipole here. So those cancel, and we'll be left with a partially positive on the carbon and a partially negative on the Cl. So, in this case, carbon tetrachloride, again, nonpolar, but CCl3H chloroform is polar because the dipoles do not cancel out. Compare the polarities of OH2O and BH3. Molecular geometry is a very important thing. Okay. See, these do not cancel out. We're going to get net movement in the forward direction. These will all cancel out with B pulling harder. Okay. Because it's trigonal planar, no lone pair of electrons there. So H2O is a polar molecule because the dipoles do not cancel out, where BH3 is a non-polar molecule because the dipoles do cancel out. Okay. There's this. Here's here. Common mistake is to forget these lone pairs on the top of S and to draw it straight. Please don't do that. So in this case, this is a nonpolar molecule because there are no dipoles. This is a polar molecule because the dipoles do not cancel out. CO2. Okay. And CO. All right. So dipole, dipole, but they do cancel out. Dipole. So this is a nonpolar molecule because the dipoles do cancel out. This is a polar molecule because the dipoles do not cancel out, leaving a partially positive and partially negative. So in summary, a molecule is polar if the dipoles do not cancel out. A molecule is nonpolar if it has no dipoles or the dipoles do cancel out. Okay, draw an interaction diagram between two H2O molecules. So we know that those are polar, partially negative, partially positive, and the other water molecule is going to be there. Partially positive, partially negative, boom, boom, boom. Okay, so this right here is the IMF. Okay, so this is a dipole IMF force right there. Two CH4 molecules. Well, you know, those are non-polar tetrahedral, so we're going to draw them farther apart as a way of conceptually noting that they have weak London dispersion. I'm just going to say LD here. Draw an interaction between one H2O molecule, partially negative, partially positive, one Na plus, so we know that the Na plus is going to go right here, and that's going to form an ion dipole, really strong ion dipole there, and one NO3 minus, and I said show the Lewis structure for that. So because it's a polyatomic ion, you need to show it in its brackets, and that's another ion dipole. So stronger than those dipoles we saw above. Okay, NH3 is going to look like this. Partially negative, partially positive. Trigonal pyramidal molecule, that lone pair pushes it into an asymmetric position, unlike BH3 up here that did not have a lone pair, thus did not exhibit any asymmetry. Okay, then we have the C. How do I want to do this? We'll do it like this. Over here, partially negative, partially positive. And there is the dipole intermolecular force. Interaction between one H2O. Okay, let's do it again. It's a really common solvent. So that's why we're going to do that. Okay, 1 SO2. So we know that SO2 is also a bent molecule, partially positive, partially negative, partially negative. There's your dipole, because there's partially charges, and then an N2 molecule, which is way over here, and there's a London dispersion intermolecular force. Justify the following statements. Water tends to be a liquid, where carbon dioxide tends to be a gas at room temperature. So I'm going to speak it. I'd like you to please write it. Water tends to be a liquid at room temperature, where carbon dioxide tends to be a gas. Water tends to be a liquid because water molecules exhibit dipole-dipole IMFs because they are polar, whereas carbon dioxide particles exhibit London dispersion IMFs because they're nonpolar. Dipole-dipole forces are stronger than London dispersion forces. Thus, it's going to exist as a liquid rather than a gas. Yeah. Sodium chloride is soluble in NH3, but not in hexane. Right? Sodium chloride is soluble in NH3 because the positive charges on the sodium will form an ion dipole force with the partially negative N on NH on 3, whereas the fully negative ion in chloride will form an ion dipole force with the partially positive H's in NH3. Hexane has all CH bonds, so it's completely non-polar. Okay, state whether you agree or disagree with this. It takes more heat to boil 100 milliliters of BH3 than 100 milliliters of pH3. I disagree. BH3 is nonpolar and thus exhibits only London dispersion forces, whereas pH3 is polar and exhibits dipole-dipole forces. Dipole-dipole forces are stronger, thus they would require more energy to break. Draw a diagram that depicts the boiling of 4 water molecules. So boiling is a liquid to a gas, okay? 4 water molecules, so let's go ahead and do that. Okay, and then all that's going to happen is those particles are going to move farther away from one another. And the reason I'm doing this is I really want to emphasize that the only thing that happens is the breaking of these bonds. That's it. Or not bonds, forces. Okay, you are not breaking any hydrogen bonds or OH bonds. I should actually be drawing all the partially negatives and partially positives and lone pair of electrons, and I know you will do that on your test. When cooled at a constant rate, which substance will condense? And this should be which substance will condense first. I apologize about that. Okay. The substance that's going to condense first is going to be the substance with the higher intermolecular forces, and the substance with the greater intermolecular forces, in this case, is water. We see that they both have the OHs on one side, and we can draw this out. But we know we're not even going to worry about this side. So methanol here can only intermolecular force form intermolecular forces with one side of the molecule right here. So it's going to have to get much, much cooler for it to form and be a solid. So water is going to be harder to boil, thus it's going to condense first. It wants to be a liquid because it's got stronger intermolecular forces. All right, it was suspected that the particular mixture contained 3 components, X, Y, and Z. To check this, the mixture was analyzed by thin layer paper chromatography. In this experiment, a non-polar solvent was used with a polar stationary phase. So this is the polar stationary phase they're talking about, just the paper. The results were obtained. Okay, so the non-polar solvent is going to move like this, and it's going to take with it other things that are non-polar. So other things that are non-polar are going to be streaked by them because they're going to intermingle because they really don't care about each other. They're less attracted to themselves than they are to one another. There's just really no attraction, but they'll still move up to paper. So they will intermingle, but they're not intermingling because they want to be with each other. They're intermingling because they really don't care, which will loosen their adhesion to the actual polar stationary phase or that paper. If something's polar, it's going to go right by it. Not because it's not attracted to it, or you don't want to think about it that way. What you want to think about is that the actual polar substance is more attracted to itself. So, which suspected components, X, Y, and Z, are in the sample? So here's the original sample. Okay, and now goes up there. So we can tell that Y is in the sample. Okay. And not really sure what's there. Okay. There is another component, but we definitely know Y is there. Okay. Are there other components? Yes, there are other components because we do see this purple phase right here. Which of the suspected components is the most polar, the least polar? So the most polar one is going to be the one that was way more attracted to itself than it was the nonpolar solvent. And that's the one that the solvent moved right past. So Z, okay, is going to be the one that's the most polar. The one that's the least polar is the one that intermingled the most with the nonpolar solvent. And then in that case, that is going to be